Hello, welcome to a new physics lesson. Today we are going to be talking about calculating lengths, areas, and volumes of functions that are going to be given in terms of polar coordinates. Okay, so I think that to introduce these kind of functions, I should speak first about functions that are in Cartesian coordinates that we already know very well, right? So, what happens if we want to calculate the length of a curve y of x in the xy plane? I mean that we have, for example, the xy axis like this, and well, we have a function that is y of x, for example, and we wonder what is the length of the curve here, right? So we know that there is a famous formula to do this. Quickly, I'm going to show you where this formula comes from. Recall that we can sketch a piece of the curve like this, and we can name this differential um, piece as maybe ds, and we can see that this element will be a differential of x and this will be a differential of y, right? Just by looking to this in an infinitesimal way, so that we get kind of like a right angle rectangle, right? Where we can establish the Pythagorean theorem in the next way. ds squared will be dx squared plus dy squared, right? Okay, so in this manner, we can factor dx squared to get 1 plus dy divided by dx squared, like this. And then from here, we can get that, well, ds is going to be dx, the square root of 1 plus y prime squared. And then you know that if we take the integral from a to b, we will get the length of the curve that we wanted to find, right? So this is the integral from a to b of 1, well, the square root of 1 plus y prime squared dx. Okay, perfect. So after saying this, I want to introduce very quickly the concept of a polar function, or a function in polar coordinates that is going to be graphed in the polar plane, okay? So what is that? I mean that, well, we can have a plane, but instead of having the x and y axis, we are going to have that in this axis, we are going to have the values of theta. So this will be, for example, theta equals to 0. Then this will be theta equals to pi divided by 2. Then we can draw maybe an imaginary line here that corresponds to theta equals to pi divided by 4, and then maybe here it will be theta equals to pi, and then here we will have 3 pi divided by 2, right? So that for every angle that we can put into the function, we will get the value of r. Okay, so for example, we can get a function r of theta, so that for theta equals to 0, we get this point over here. Then for theta equals to pi divided by 4, we will get this point. And for theta equals to pi divided by 2, maybe this point. I don't know, we can have many of these functions, right? So that, for example, we can join the points and then we get a curve, but now in the polar plane, right? So it's just a different way to graph a function. Okay, perfect. So in the same manner, we wonder what will be the length of a curve in Cartesian coordinates. We can wonder what will be the length of the curve, but now in the polar plane, right? So we can say that if we start at theta equals to 0, the curve grows in a counterclockwise way, right? So that our interval of integration is going to start from theta equals to 0 and then to the final angle where we want to measure the length. I mean that, for example, if we want to measure the length from here to this point, which is the point from theta equals to 0 to theta equals to pi divided by 4, then this length will correspond to an integral whose limits of integration are going to be theta equals to 0 and theta equals to pi divided by 4. Okay, but how are we going to construct the formula that corresponds to the length of that curve? Okay, well, looking that this is r of theta, well, we need to express the same exactly formula that we had for y, but now for r, right? So how will that be? Well, we can start again by the concept of ds squared equals dx squared plus dy squared, right? But knowing that we know what is the transformation between Cartesian and polar coordinates, and those are x equals r cosine theta and y equals r sine theta, right? So we are interested in calculating the x and the y. So for the first example, will be dx equals dr cosine theta minus r d theta sine theta. This is from basic calculus. It's just calculating the total differential. And then for the y will be dy equals dr sine theta plus r d theta cosine theta, right? So we calculate these quantities squared. That will be dx squared equals dr squared cosine squared theta minus 2r sine cosine dr d theta, and then plus r squared d theta squared sine squared. Okay, and then for y we will have the y squared equals dr squared sine squared theta plus 2r sine cosine, and then dr d theta plus r squared d theta squared cosine squared theta. So looking that we need to sum these two quantities, we cancel this element with this element, and we see that we have cosine squared plus sine squared. That will give us, well, if we sum, we will get that ds squared is equal to dr squared plus r squared d theta squared. Recall that ds squared is equal to dx squared plus dy squared. Okay, perfect. So I think that with that, we have already our differential element of length corresponding to the polar function r of theta. But we will be interested in presenting this as, well, the differential of theta times some other function, right? So we can factor d theta from here to get that ds squared is equal to d theta squared times dr divided by d theta squared plus r squared. Okay, and then from here we get that ds is equal to the square root of r squared plus the derivative of r with respect to theta squared and then the theta. And as you should guess, we are going to integrate this from the initial angle to the final angle of the curve to get the total length of the curve that we want to measure. So that is s equals to the integral from an initial angle theta 1 to a final angle theta 2 of the square root of r squared plus the derivative of r with respect to theta squared times the theta. Perfect. So I think that with this we have already a first result that is important. So this will be equal to the length of the function in polar coordinates in the polar plane, right? Okay. Yeah. And other thing that I think it is worth to mention is that from this definition of ds squared, right, instead of factoring d theta squared, we can factor dr squared. So we will get ds squared equals to dr squared times 1 plus r squared, and then we will have the derivative of theta with respect to r squared like this. So following the same steps, we will get that s is equal to the integral from one initial radius r1 to final radius r2 of the square root of 1 plus r squared, the derivative of theta with respect to r squared, and then dr, right? Perfect. So it's just to well, exactly the same that we found before, right? But now in terms of an integral with respect to r. So you may be wondering what happens with this r1 and r2. Well, if we said that when we were calculating the length of this curve, we start on an initial angle theta equals to 0 to a final angle theta equals to pi divided by 4. Now we are going to start from an initial radius that is going to be the radius corresponding to the initial point of the curve, right? So that radius will be this one over here. Yeah, so it's the value of the function at theta equals to 0. And then the final radius, of course, it will be this one over here, which is the value of the function at theta equals pi over 4. So those will be the limits of integration in case you want to use this formula. But let me tell you already that actually I think that in almost every exercises that you will find, these formulas are for well, it is more convenient to do it for theta. Okay, I think it's the more used way you can find. Okay, perfect. So this will be the way to calculate the length of the curve in the polar plane. Perfect. So what happens if we now want to calculate not the length but the area that is enclosed by the curve, right, between 2 points and the origin, right? We can be interested in doing that, maybe. So, as an inspiration, we are going to talk about first about a circle, right? We know that the area of a circle is, well, pi r squared, right? And that a circle corresponds to a 2 pi angle. But what happens if we want to measure just a piece of circle, right? Like this. Recalling that we are measuring these distances from the origin. I mean that these are the radius of the circle. That's important. Okay, and then we open this piece with an angle theta, right? Well, we know that, for example, if the total area of the circle corresponds to pi r squared, that corresponds to 2 pi. Well, we wonder what is the area corresponding to an angle theta, right? So just by the multiplication rule that you all know, we will get that this area is equal to theta pi r squared divided by 2 pi. And then this area of theta is equal to, well, theta r squared divided by 2, which is a very well-known formula. So the thing here is that this is an inspiration, but to think it of a curve in the polar plane. I mean that instead of having a circle that has a constant r all the time, we will get an r that is changing with respect to the angle theta. Okay, so instead of having a circle, we can maybe have this curve, and we can measure a point from the origin of the polar plane that will be given by the function r of theta. And then we can have maybe a different point for a different angle, r of theta over here, right? So we can think of an infinitesimal piece of curve like this that can be measured with an r of theta over here. But looking that it is an infinitesimal piece, this can be d theta, right? So looking or thinking that it can be approximated to as the area of a piece of circle, and we can say that the area of this piece is going to be 1/2 of r of theta squared times d theta. Okay, so as you should guess, to establish what is the total area of the piece that we want to measure, well, we need to integrate from an initial angle to a final angle. Again, if we would like to calculate this area over here, well, we may need to integrate that function that we found from theta equals to 0 to theta equals to pi divided by 4. Okay, so that means that the area of The area enclosed by the curve r of theta will be the integral from an initial angle, theta 1 and theta 2 here, of 1/2 r of theta squared and then d theta. Perfect, so I think that this formula was easy to find. Okay, so I think that's already an important result. So now we are going to be interested in finding the area of the surface of revolution, but in polar coordinates. I mean that for this polar function, right? So we are going to take the concept from Cartesian coordinates and then we are going to transform it to polar coordinates. I think that will be the easiest process to follow. So again, we are going to sketch this in Cartesian coordinates to remember what's the process we follow to find these kind of things, right? So we have a function in the xy plane given by y of x, right? And we want to measure from A to B the area of the surface of revolution that is a result of rotating this curve around the x-axis, for example. Yeah, it can be also around the y-axis, but for now, for simplicity, we are going to consider only the x-axis rotation. So if we do that, we are going to get a three-dimensional surface like this. And again, we want to calculate the area of the surface, right? So to do that, we are going to consider an arbitrary point x, right? That will help us to generate a cross-section of the figure, right? So that we can calculate the perimeter of the circumference that is formed in this x value, right? So if we know what is the perimeter of an arbitrary cross-section at a point x, then we can multiply that perimeter times differential s of the curve, right? So that we will get a differential element of the surface, right? Kind of like this, maybe. And we want to calculate the area of the surface, right, of this differential element. Okay, perfect. So in polar coordinates, we have seen that we can define a differential element of the curve as, let me recall that it is in this manner, right? ds equals to the square root of r squared plus the derivative of r squared times d theta. So that is what we are going to use again. So ds is equal to the square root of r squared plus the derivative of r with respect to theta squared d theta. And we can calculate the perimeter of this circle by saying that, well, we know that the formula of the perimeter is equal to 2 pi times the radius, right? But at the point x, the radius will correspond to the value y of the function, right? So this is equal to y, actually y of x, right? So we know that the perimeter of that circle will be 2 pi y. And then the area of that differential element of area is going to be 2 pi y times ds. Okay. Okay, so in Cartesian coordinates, we will get that the area of the surface of revolution will be the integral from a to b of 2 pi y times ds, right? But that is 1 plus y prime squared dx. Perfect. Okay, but in polar coordinates, we will get that looking at our ds is a function of r and theta, but it depends on a differential of theta. The limits of the integral will be angles, right? So this will be the integral from an initial angle to a final angle of 2 pi y, but y in polar coordinates is r sine theta. So this is r sine theta. And then ds, but ds is equal to the square root of r squared plus the derivative of r with respect to theta squared, and then d theta. Okay, perfect. So, yep, I think this will be the final formula for the area of the surface of revolution, but to the curve r of theta in polar coordinates. Okay. Okay, so just to finish, we are now going to find what is the formula for the volume. Again, by inspiration in Cartesian coordinates. So we know that, again, if we have the x-axis here, the y-axis here, we have a curve that we are going to measure the length from A to B. Then we have that cross-section like this at a point x. We'll have a radius y of x, right? In this case, we are going to be interested in calculating the area of the cross-section, right? Not the perimeter, but the area, because we are going to find the volume of the surface. Okay, so that area will be pi times r squared, but the radius is y, right? So it is pi y squared. Okay, perfect. And then to get a volume, we need to multiply by a differential of length, right? So that this quantity has a volume. So the volume will be actually a differential of volume, right? A volume element will be pi y squared dx. Perfect. So that if we want to find the final volume, or the total volume, I should say, this will be the integral from a to b pi y squared dx. Okay, perfect. So how can we translate these to polar coordinates? Well, we will have that, looking at x is equal to r cosine theta, dx is equal to dr cosine theta, and then minus r d theta sine theta, right? Okay, then from here we can follow two ways. We can factor a dr, or we can factor a d theta. Looking at working with integrals of theta is more common, and I think more convenient also. We are just going to give the result for the integral of theta. So that means that we are going to factor d theta. But I think that will be a good exercise for you to see what formula do we get if we factor dr, right? So this will be d theta times the derivative of r with respect to theta, cosine theta, minus r sine theta. Okay, so that is dx, right? And then our volume will be an integral that it will be now for an initial angle theta 1 to a final angle theta 2 of pi y squared, but y squared is equal to r sine theta squared, and then dx, but that is the derivative of r with respect to theta, cosine theta, minus r sine theta, times d theta, right? Okay, recall that, again, we have a curve that is in terms of theta of the form r of theta, right? Okay, perfect. So I think that this is the final important result of this lesson. So it is, again, the volume that is generated by a revolution of the curve r of theta in the polar plane, right? Okay, perfect. So I think this is the final important result of the lesson. I hope you liked it, and thank you so much for watching.